This is a picture of the atom. The electron cloud surrounding the nucleus gives an atom its chemical properties and is the realm of the chemist. Physicists are concerned with the nucleus of the atom. The nucleus is made up of two types of particles, protons and neutrons. These are present in nearly equal numbers. The general term for a proton or a neutron is a nucleon. Protons are positively charged, neutrons have no charge. No one has yet worked out a model of the nucleus that fits all the facts. The proton model assumes it is made up of a mixture of protons and neutrons. The shell model assumes they are in layers. Another model or view of the nucleus is the liquid drop model. This assumes the nucleons are free to move elastically. The density of nuclear material is 100 million times that of water. If you were reduced to one nucleus, you would only be a few microns in diameter, but you would have a short life, exploding before the new element could be named after you. The shell model assumes the nucleons are in shells, with complete shells being particularly stable. The nucleus is not uniformly hard like a billiard ball, but has a fuzzy surface due to a variation in the density of the outside layer of nucleons. Let's look at the atomic mass unit, or AMU. The atomic mass unit is the average mass of a nucleon in carbon-12. Nucleons vary in different nuclei depending on how much mass is lost as binding energy. The mass of the electrons is so small it can usually be ignored. It would take over 1,800 electrons to have a mass equal to just one proton. The neutron is slightly heavier than the proton. The difference in mass is the mass of just over 2.5 electrons. There are several abbreviations used to describe the number of protons, neutrons, and atomic mass of the nucleus. The neutron number N represents the number of neutrons in the nucleus. The atomic number Z represents the total number of protons and hence the total positive charge on the nucleus. It will be equal to the number of electrons. The atomic mass number has the symbol of A. It is the total number of nucleons in the nucleus. The correct way of identifying a nucleus of carbon is to show the atomic number on the bottom left and the mass on top. However, it is usually abbreviated to simply C13. Nuclei of an element can have different numbers of neutrons, and these are isotopes of the elements. Carbon, for example, can have 6 neutrons, or 7, or 8. However, carbon-14 is not stable. In the first 92 elements of the periodic table, there are around 250 different natural isotopes. When a neutron is added or removed, many nuclei will become unstable and disintegrate. This graph shows the combination of protons and neutrons that are stable. Everything outside this range is unstable, which means radioactive. For stable nuclei up to around calcium with 20 protons, the neutron-to-proton ratio is close to 1:1. Protons and neutrons probably bind in pairs. However, as the number of protons increases, the electrostatic or Coulomb repulsion force builds up. These heavier nuclei need extra neutrons to dilute the greater Coulomb force. Eventually, at 84 protons, which is polonium, there are too many protons pushing each other apart, and all elements past here are radioactive. There are no stable nuclei with 84 or more protons. Elements from polonium-84 to uranium-92 are all naturally radioactive and are found in the Earth's crust. Elements with more than 92 protons are too unstable to be still present on the Earth. They can be made artificially, but they will break apart. The forces within the nucleus are still being researched. The world is made up of particles and waves. All particles emit waves of some sort. Charged particles emit photons of electromagnetic waves. Coulomb force is caused by an emission of photons. In this case, the protons are repelling each other. But there is also an extremely powerful but short-range nuclear force attracting a pair of nucleons to each other, no matter what their charge. Neutrons and protons are made up of quarks, and quarks emit nuclear field waves called gluons. The rapid exchanging of gluons holds each quark inside the nucleus. Occasionally, quarks leave the nucleus, but they can only do so as a quark-antiquark pair called a pion. This exchange of pions holds each nucleon within the nucleus. The nuclear attractive force is maximum at an optimum distance. Any closer, the nuclear force becomes repulsive. The total nuclear force in a nucleus does not change even if the number of nucleons changes. So, helium is held together with the same force as the large nucleus of uranium. However, the Coulomb repulsion force varies not only with distance, but with the number of protons. This is why large nuclei are unstable. They will break apart until there are a stable number of protons remaining. If a neutron and proton are combined, energy is given off. In this process, mass is lost as energy. The final atom on the right is lighter after combination than before. There is a mass defect. The mass missing was converted to energy, nuclear energy. The energy can be calculated using Einstein's famous equation E equals mc squared, where E is the energy, m is the mass lost, and c is the speed of light. The amount of energy given off is called the binding energy. And in reverse, this is how much energy it would take to break the two nucleons apart. This graph shows the average binding energy per nucleon against the mass number A. The binding energy per nucleon rises rapidly to a peak at iron, which has the most stable nucleus. It would take a lot of energy to break it apart. As the nuclei get heavier than iron, the average binding energy declines because of the buildup of the Coulomb repulsive force between the protons. Let's examine mass numbers 20 and less. For the light elements, we have a series of stability peaks 4 nucleons apart. Helium at 4, beryllium 8, carbon 12, oxygen 16, and neon 20. This suggests that stable nuclei may be made up from multiples of 4 nucleons, which is the helium nucleus, or alpha particle. So the most stable nuclei are helium-4, beryllium 8, carbon 12, oxygen 16, neon 20, magnesium 24, silicon 28, sulfur 32, argon 36, calcium 40, and so on. No one is quite sure of why 4 is so critical for stability or how the nucleons fit into the nucleus. However, the stability of their other isotopes with more or less neutrons is different. In many cases, an extra neutron would make the nucleus unstable enough to break apart. It would become radioactive. As we saw earlier, of the 92 naturally occurring elements, all of those with 84 protons or more are radioactive. Elements with more than 92 protons are too unstable to be still present on Earth. A radioactive nucleus contains too much energy. It will spontaneously break down or decay to a more stable state. As part of this process, the nucleus releases its extra energy as radiation. This radiation has several properties. It will ionize gas molecules, making them detectable with a Geiger-Müller counter. It exposes photographic film. It makes certain crystals glow or fluoresce. Some of the radiation from the nucleus damages living tissue, which is part of the horror of its use in war, and its benefits in sterilizing food. It's used to kill bacteria that would consume the food. The problem is, it also knocks electrons off atoms, forming free radicals, which may or may not cause cancer. There are three types of ionizing radiation from the nucleus. Alpha radiation is helium nuclei, beta radiation is electrons, and gamma radiation is high-energy electromagnetic radiation with more energy than X-rays. Each is named in the order of discovery. When a nucleus gives off an alpha ray, it is sending out a helium nucleus of 2 protons and 2 neutrons. They are relatively slow-moving with an initial velocity in the order of 1/20th of the velocity of light. Because they have a positive charge and large mass, alpha particles produce intense ionization as they move about in a gas. Alpha particles have a range in air of 2 to 10 centimeters. Despite their energy, they do not go far because they use up so much energy in ionizing the molecules. They are easily stopped by air or the outer layers of skin. It's not a dangerous radiation. When an alpha slows down sufficiently, it will capture 2 free electrons and become a normal helium atom. The volume increase would of course be far greater than this. Sometimes the nucleus will give off electrons, and these are named beta rays or beta particles. Since electrons do not exist within the nucleus, they're most likely created when a neutron is transformed into a proton, and along with the electron comes an antineutrino. Beta particles may be ejected at a continuous range of velocities up to 98% of the velocity of light. They can penetrate longer distances than an alpha particle. A fast beta particle can traverse nearly a meter of air or a few millimeters of aluminium before its energy is lost. Even after a radioactive nucleus has emitted an alpha and/or a beta particle, it often remains in a highly excited energy state, and if so, the nucleus emits gamma rays to gain maximum stability. Gamma rays have neither mass nor charge. They are photons of energy in the form of electromagnetic radiation. These have the same physical nature as light, X-rays and radio waves. They have a very high frequency with a short wavelength in the order of 1/100th that of X-rays. They are far more penetrating than X-rays. Gamma rays are more penetrating than either alpha or beta particles. They can penetrate very large thicknesses of material, such as several centimeters of lead. The half-life is the time it takes for half of the nuclei to decay. It will then take the same time for half the remaining nuclei to decay. Half-lives range from fractions of a second to billions of years, but is constant for a particular isotope. For example, an isotope may have a half-life of 2 days. This means that after 2 days, its disintegration rate will be half. After another 2 days, half again, and so on to the last nucleus. Transmutation is the changing of one element into another. This combination of nucleons is lithium. With an extra proton, it would be beryllium, and with another, it would be boron, and so on. If this imaginary nucleus split in half, the number of protons in each part would determine which element each had become. A nucleus decays when it has too much energy to be stable. If the decay emits an alpha particle, it is called alpha decay. An example of alpha decay occurs when a nucleus of radium decays by emitting an alpha particle. It now becomes radon, the last of the noble gases. The second type of decay is beta decay, where a beta particle, an electron, is emitted. If a nucleus has too many neutrons, one will spontaneously convert to a proton. An electron and an antineutrino will be ejected from the nucleus. This is called beta decay. The neutron is made up of three members of the quark family. One of these holds a positive charge of plus 2/3, and the other two hold a negative charge of minus 1/3 each. During beta decay, one of the negatively charged quarks gives off an electron and a neutrino. The quark is left as plus 2/3. The total is plus 1. An example of beta decay occurs naturally in the upper atmosphere, where neutrons in the form of cosmic rays bombard nitrogen. Most nitrogen has 7 protons and 7 neutrons. When the neutron from the cosmic ray joins the nucleus becomes nitrogen-15, which is unstable. A proton is then given off, and the nitrogen changes to carbon-14. But carbon-14 too is unstable because it has too many neutrons. One of the neutrons eventually turns back to a proton, and we end up where we started, with nitrogen-14. Beta-positive decay only occurs in nuclei with an excess of protons, and none of these is naturally occurring. One example is the artificially produced isotope of nitrogen-13. It has too many protons to be stable, so one proton gives off its charge in the form of a positive electron, or positron. It will also give off a neutrino. With one less proton, it has transmuted to carbon, in this case carbon-13. Even after ejecting an alpha or beta particle, the nucleus may still have too much energy to be stable. It will then give off a gamma ray. We can cause a nucleus to break up by bombarding it with particles. If the new nucleus is unstable, it will decay. The remaining nucleus may be a stable isotope, or it may, in turn, decay further. When the nucleus of aluminium-27 is bombarded with alpha particles, there is a transmutation into an unstable isotope of phosphorus. It is a radioisotope with a half-life of 2.5 minutes. It will decay into a stable isotope of silicon. The second part is a beta-positive decay where a positron is emitted. The first artificial transmutation was carried out by Rutherford, who bombarded nitrogen with alpha particles to produce oxygen. Nuclear fission means the splitting of a nucleus into 2 smaller parts. If a large nucleus, such as uranium-238, captures a slow-moving neutron, it will start to wobble. There is Coulomb repulsion force between the 2 positively charged ends, which overcomes the nuclear force. As uranium decays down to lead, we see both alpha and beta decay. First, an alpha particle is emitted to reduce atomic number by 2 to thorium. Then atomic number is increased by 1 with a beta decay to produce proactium, beta decay to produce a lighter isotope of uranium, then alpha decay back to thorium, alpha decay to radium. and again to radon. Same for polonium. And lead. Then beta decay to bismuth, another beta decay to polonium again, then alpha decay to lead, beta decay to a light isotope of bismuth, another beta decay to another polonium, then alpha decay to produce a stable form of lead.